Okay.
Hello, hi everyone. Good morning, good afternoon, good evening, wherever you are. It's our pleasure and honor to host you this week with another geoscience and geoenergy webinar. Sebastian Geiger from Heliot Watt, myself from TU Delft, where I actually literally am speaking. I am today in office, so it's very good to be back. I wish you all the very best, those who are back in office and those looking forward to be back in office. A good time. So today we have the pleasure and honor to host our colleague, Professor Nicolas Espinoza from UT Austin. Nicolas is an associate professor in the Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. He earned his civil engineering diploma from the National University of Cordoba in Argentina in 2006. And I did some search about this university, by the way, so to just introduce you that this university, if you did not know, was founded in 1613, more than 400 years ago. And if you can guess how many students this university has, I could think that you might be wrong. It has more than 111,000 students. 1,100,000 students. So it's impressive. And at TU Delft, we have 25,000 students. Sebastian, how big is Heriot Watt? Number of students. Can you unmute yourself?
Yeah, sorry, about 30,000.
Okay, so we are about TU Delft size. So very nice. So with that, he obtained after his diploma in Argentina, he obtained his master's and PhD degrees both from Georgia Tech, Georgia Institute of Technology, in 2008 and 11, respectively. His primary research interests include mechanics and physics of natural porous media, granular media, and fractured rocks in the context of advanced subsurface completion techniques, reservoir geomechanics, geophysics, and formation evaluation. The main fields of application of Dr. Espinoza's research are energy recovery from unconventional reservoirs, carbon geological storage, and geothermal energy. Nicolas has co authored over 90 technical articles, served as an expert reviewer for several scientific and engineering journals, given seminars at various leading research and educational institutes, and promoted the important topic and discipline of geomechanics education through free online resources, including our geoscience and geoenergy channel. And we are pleased and honored, delighted, Nicolas, that you accepted our invitation to give this lecture today. Thank you for accepting our invitation. To the audience, please note, like always, the lecture would last for about half an hour, followed by questions and discussions. Like always, again, you know the deal. Please type in your question in the chat box, and at the end, Sebastian will go through them. Do not wait until the end of the talk to post your questions. Whenever you feel appropriate, please do so. Your question may trigger other questions as well. And by the way, one also side note here, we have released an 8-minute long video about the geoscience and geoenergy webinars and also disciplines. We will post a link to those of you who have not yet noticed it. So without any further ado, Nicolas, thanks once more for accepting our invitation. The stage is all yours.
All right. Thank you very much, Hadi. Thank you very much, Sebastian, too, for inviting me to this webinar. Let me go ahead and go to my PowerPoint screen. All right. So I guess now can you please confirm that you can see my screen? You can hear me well? I guess you do. Okay. So today I have the pleasure to share with you a recent study
Nicolas,
that
I'm
we did.
sorry, we do not see your PowerPoint yet.
Okay. So you do not see my PowerPoint.
Yes, can you click on the PowerPoint?
What about now? No?
No, not yet.
What about now?
No, maybe you can unshare and share again.
Okay, I'll try that.
So go to the PowerPoint, the slide.
Well, now.
I don't think that this is your, it's your browser that we see.
My browser.
Yeah,
Okay,
it's your Chrome browser or Firefox. If you can minimize that, maybe we can see your, or maybe you're not sharing the right screen.
All right, let me try again. All right, well, now.
Yes, absolutely right. So, okay, so you press the presentation, please, and take it. Yep.
And now you can see full screen. Correct?
No, we just see it as a presentation yet with notes on it, etc. Not in the presentation.
Okay, let me give you one more try. I guess I should have done this with Chrome instead of Firefox as we tried yesterday. But I think this time I'm gonna succeed. Well, I'll go entire screen, and now it should work. You see my PowerPoint presentation now?
We do see it.
And now you see full screen.
Fantastic. Excellent. Please start.
All right, great. Okay, well, then now we can start. Good afternoon, good morning, good night, good evening, everyone. Today, I'd like to share with you a study about pressure monitoring above the injection zones for CO2 geological storage that we did with a former student of mine, Charjin Zheng, now a postdoc at Princeton, and my colleagues Matthew Van Dam and Jean-Michel Pereira from École de Pont. Well, you know, this study actually, for those of you that are in Europe, has kind of a European flavor. Not only because of my colleagues, Mathieu and Jean-Michel from École de Pont, but also because many of the theory behind this work, I learned it when I was a postdoc at École de Pont. So I'm very glad to share this with you, particularly with people in Europe that are familiar with this topic. Well, before I start, let me tell you just a little bit about myself. I did my PhD at Georgia Tech, like Hadi said. Then I moved to France. I did my postdoc at École de Pont. And since 2013, I'm associated with the University of Texas at Austin, working in a variety of energy topics. And my research combines both experimental work and analytical and numerical simulation work. I do all of them. I think all of them are important, and I think they inform each other. Each discipline informs the other, so it's very important to get to know about everything. And today, I'm going to talk mostly about simulation work. Before I start, let me set up the stage by saying that we have a great challenge. We as a society, as a world, have a great challenge, which is to produce abundant energy. But this has to be low carbon, has to be cheap and affordable, especially for countries which have to develop more. And it also has to be reliable. And that's not easy at all. That's not easy, but that's what we have to work on. That's our challenge, and we have to engage on it. And one of the solutions for that is carbon geological storage. It's not the only one, but it's one of them. And I believe that in order to transition to a future where we have low carbon technologies, we have to go through this transition in order to enable other sources of energy to jump in and take a little bit more of share of the energy production that we have today, mostly from fossil fuels. We see today that there is another player in this scenario, which is hydrogen, which is going to help, I believe, in going through this transition and making things good for everyone. I also wanted to share with you recent post that I saw from the Geological Society of London. I like this one very much because it tells you that wherever you are in geoscience, there is something that you can do for the future and for a cleaner future, for a more sustainable future. And I'm not going to go through all of these, but I encourage you to check this post and just see where you can see yourself. And this is how I see myself. These are the things I do. And today I'm going to be talking mostly about carbon capture and storage here on the right. Let me bring the laser pointer. All right. Okay, talking about carbon geological storage, we have many challenges in carbon geological storage, like, for example, achieving high injection rates, maximizing the storage capacity, quantifying well the storage capacity, and monitoring where CO2 goes after injection, making sure that the seal remains a seal at all times, and also to do that in a cost-effective manner. More from the point of view of geomechanics, here are some of the implications that we have when we inject CO2. When we inject CO2, CO2 pressurizes a reservoir, and that changes the pressure not only in the reservoir but also outside the reservoir, and also that produces stresses or changes the stresses around the reservoir too, in the caprock, in neighboring faults, even beyond the caprock. And most of the research, and probably that you're familiar with, is about fault reactivation due to injection of a fluid, in this case CO2. And here we pressurize too much. Some of these faults might reactivate. Depending on the properties of the fault, that might create a seismic emission or not. In some cases, some of those faults, depending on the permeability and evolution of permeability with reactivation, those might let CO2 migrate if CO2 gets there or not. And those are very important things to consider in order to make CO2 storage and utilization effective. Today, I'd like to share with you another consequence of CO2 injection, which is changes of pressure in the caprock and above the caprock. And we'll see what are the opportunities of this for monitoring and also for checking seal integrity. I'm going to start with an example, just for you to trigger your thoughts and see if you can find the solution before I show our solution. So this is an example of CO2 storage in Cranfield, Mississippi. This was conducted. I'm not quite sure how well you see the screen, but hopefully you see here these contour lines. This is a dome. It had oil, and it's a field that was producing for a long time. There are several wells in the region, and in the water leg that is below the water oil contact line, 3 wells were drilled, completed, and also equipped with monitoring devices in order to track the injection of CO2. So this is mostly a NEOR field, but here my colleagues from the Bureau of Economic Geology and also from the CCARB partnership, they took advantage of this field to put a CO2 injector, put 2 monitoring wells, and they did a lot of monitoring in these 2 wells. I'm just going to talk about one particular monitoring, which is placing pressure and temperature sensors above the caprock. So here, this is injection zone, right? This is the injection wellbore. These are the monitoring wellbores. They put pressure and temperature sensors here above the caprock. So what is the idea here? Well, if there is any migration of brine or CO2 through the caprock, you should see that as a spike of pressure above the caprock, right? That's what we would normally think. Well, let's look at the data. Here you have the injection rate and temperature at the injection wellbore. What they did here is to inject CO2 in 3 stages, similar to a step rate test. And here you have the pressure response at the wellbore. Let me add here a few lines just to help your eyes to follow what's going on. The lines are showing when injection was either ramped up or was resumed after being stopped. And here you have the pressure signal. And as you might expect in the injection zone, as you ramp up the pressure, I'm sorry, as you ramp up the injection rate, pressure increases, like right here, here a little bit more. And this is more or less what you expect. You inject, pressure goes up. Well, let's see now what happens above the injection zone. And before I do that, just try to think what you would expect. All right, here we go. This is what was measured. In these two wells, the signature was a little bit different. And pressure in monitoring well 31F2 increased steadily, and pressure in the other well further away, it didn't increase steadily, but rather shows some spikes with each change of injection rate, like you see here. And there we don't have data before, so we cannot tell anything, but also you see here. So what's going on here? What's a problem with this, or is there any problem with this signature? Is this what we expected? What would you expect? Is there here migration of either brine or CO2 through the wellbore or not? Well, this is what we're going to try to answer in this presentation. Before I go to that, let me share a little bit of theory and an extension of what some of you might know or some other you might not know very well. So going to the basics of fluid flow in a porous medium, if we have our incompressible single-phase fluid flow equations, we write the continuity equation. If there is no change in porosity, if there is no change in density of the fluid, that will be the incompressible part. And assuming that we have an isotropic and homogeneous permeability everywhere, then we arrive to Laplace's equation, right? Most of, all of us, we know that. And here our variable is pressure. Okay, let's go to the next step. Let's assume now we have a slightly compressible fluid. Well, now we have a storage term in which the density of the fluid can vary. So we cannot neglect that term anymore. And after adopting a model for the density of the fluid as a function of pressure, we can write our equation just as a function of pressure, and we recover the diffusivity equation, right? Which is right here and depends on the compressibility of the fluid. All right, we're still solving for pressure only, but we have one additional property of the fluid, which is the compressibility. Let's go one more step. Now we are going to bring poroelasticity into the equation. Now we have storage by a variation of porosity and also by a variation of density of the fluid. And by using the theory of poroelasticity, I'm jumping here a few steps, I can replace this term over here by this term over here, where I include the variation of porosity, or I write the variation of porosity as a function of the variation of the volumetric strain of the entire porous medium. And also I bring the compressibilities here. M has a compressibility of the fluid and also the compressibility of the mineral phase. That means that the mineral can also change volume. And I put all of that together and I recover the diffusivity equation for a poroelastic solid, in which now, instead of just one variable, which is pressure, I have two variables. I have pressure and I have volumetric strain. So what is this volumetric strain? Or where do I get it? I get it from the poroelastic equations of effective stress, which tell me that volumetric strain not only depends on pressure, but also depends on stress. So external stresses can cause a volumetric strain, and changes of pressure can also cause changes in volumetric strain. But those are two independent things, and I need to consider separately in a fully coupled solution. So you might have thought, well, I can include the raw compressibility just by modifying this factor here, instead of compressibility of the fluid, just use compressibility of the rock. And that solves the problem. I don't need poroelasticity. Well, that's not quite true, because when you do that, you assume that the rock deformation just depends on pressure. But as we see in the fully coupled solution, the rock deformation also depends on stresses. And sometimes you can change stresses by changing pore pressure, or you can change pore pressure without changing stresses. And this is the equation that we need in our case. And this is the equation which is going to let us solve the problem that we saw before. All right. So now that we know the theory for this, let's go ahead and see now how we can attack this problem of monitoring above the caprock, or also monitoring above the injection zone. All right, so let's say that we start injecting CO2 in this formation. The formation has some faults which are neighboring the formation, some of them that we can see very well, some others that we might not see very well. We start injecting, let's say, at the constant injection rate. What would we expect, as we said, that the pressure in the injection zone will increase? All right, so far so good. What's going to happen above the injection zone? If we do not consider the deformation of the rock, we might think, well, if there is no migration of any fluid through the caprock or through a fault or through the wellbore, then the pressure should not increase. Well, this is actually not true. The pressure might increase a little bit. And even if there is no fluid flow across the caprock or fault. And that's what I'm going to show today, the theory I'm going to show today, data that support that, and also how we can take advantage of that for monitoring. So let's bring now poroelasticity. Now we know this extended equation of poroelasticity. And what poroelasticity tells me is that I can have changes of pressure due to a volumetric strain of the rock without a fluid migration into a particular formation. So let's imagine that this piece of rock is here above the caprock, and I change the pressure in the injection zone so the rock deforms over here. The question is, what is going to happen with the pressure in the rock? And the answer is going to depend on several properties, mostly on the permeability and the compressibility of the fluid. But let's say that this process of injection applies a volumetric strain, makes the rock smaller, and what is the response going to be? Well, the change of pressure is going to be dictated by this equation. This would be the prediction for what is called a fully undrained scenario, in which as I compress a rock, the fluid has nowhere to go. And this is the case, for example, when the permeability of the rock is very low, like for example, in a shale. You can compress a shale, but the fluid has no time to escape. That's the case, for example, very common for overpressure in many offshore places. So if the fluid has nowhere to go, then pressure is going to increase. But as permeability increases, the change is going to vary. It's going to go from fully undrained conditions to fully drained conditions. For a rock with very high permeability, and if I apply a volumetric strain at a given rate, probably if I do it slow enough, applying the volumetric strain, the pore pressure might dissipate at the same time or even faster than I apply the volumetric strain, and I'm not going to see any increase of pressure. But this is exactly what we want to capture. We want to capture what is going to be the increase of pressure caused just by deformation of the rock above the caprock. Okay, so let me tell you how we solve this problem. First of all, we created a synthetic model, very simplified, mimicking some of the structures that we see in the Gulf of Mexico, sequences of shale and sand. Here you have one example. And let me move this a little bit so you can see the reference over there. And we created the model based on this scenario. And let me bring back here this to my presentation. This is the model. It's a three-dimensional model in which we have an injection zone, we have a caprock, and then several monitoring layers, which we call above injection zone layer, or AIC, 1, 2, 3, 4, 5, in which we monitor pressure, sometimes along the wellbore, sometimes further away from the injection wellbore. But in this case, we're going to start with monitoring in the injection wellbore. So here also you see the properties of our formation. We did these simulations with a software called CMG Gem. This is coupled with Poroelasticity iteratively. But the important thing is a two-way coupling. Sometimes in some software you see just a one-way coupling where, for example, a change of pressure can or a change of stress can affect the change of porosity and permeability, but it doesn't fully couple the equation that we saw before, where a change of stress cannot change a pore pressure. Well, in this case, it's a two-way coupling. So if we have a change of stress and a change of strain, that can cause a change of pore pressure, as we saw previously in the theory. And let me show you, go ahead, with the base case. So with the base case, we inject into a reservoir layer and with a constant injection rate for some time. And before we go to the other more subtle changes, let's see what we would expect when we inject in this reservoir. What are the changes, particularly from the geomechanical point of view? So if we inject in this reservoir, then what we would expect is a decrease in effective stress in the reservoir, which causes a deformation around the reservoir. That causes the formations above to move, and actually to move upwards, right? Sometimes these changes of pressure can be so large, and also depending on the thickness of the reservoir, that even they go up to the surface. And that's when we observe, for example, surface heave. There are some places like the Insala project where that heave was quite a bit. And what I hope that you see from here is that we don't have to go to the surface to measure some of these changes caused by the injection of CO2. Actually, the changes also happen halfway between the reservoir area and the surface. And this is what we're going to try to catch in this study. Let me also bring this to your attention, particularly for the people that know are experts in fluid flow, and probably may not know that much about geomechanics. We know that in fluid flow, a gradient of pressure brings flow. In mechanics, a change of displacement, like we see over here, brings strains or produces strains. So what we're going to see here are deformation of the rock above the caprock. All right, that deformation of the rock above the caprock is what is going to cause a change of pressure above the caprock, even though there is no fluid migration at all from the injection zone to the regions above the injection zone. So what I'm going to show here is that variation of pressure. Notice it is in logarithmic scale. So here is the injection layer, caprock in between, and we have the monitoring layers above the injection zone. So again, this is a constant rate injection. The bottom hole pressure is more or less constant too, and this is what we see. Let me now bring my pointer. This is what we see. This is a movie of the result. As time passes by, pressure, of course, increases in the injection zone, but also increases outside the injection area. Notice something very important here. Now, at the end of time, what the regions which are sort of light up with higher pressure are the shales. But let me start this over, and you will see that at the beginning, the regions that light up are the sands. That as time passes by, pressure decreasing in those areas and just stays in the shale. So what is happening here is that the deformation of the rock outside the injection zone is causing deformation everywhere in shales and sands. Here we have the results of change of pressure in the sands, but also happens in the shale. The thing here is that we cannot really monitor changes of pressure in the shale because they have such a low permeability that such a measurement is very difficult. So instead, we want to measure changes of pressure in the sand. Also because if there is a leak, as we're going to see later, it's going to be more readily observable in those locations. So in these injection layers, this is what the simulations predict, that even without, again, any migration of either brine or CO2 above the injection zone, we see an increase of pressure. An increase of pressure is relatively small, in the order of tens of kPas, but it is measurable. And also, it is a function of time, as you can see how this increase, go to a peak, and then decrease depending on time. This depends, as we saw before, in the permeability of the formation. But it's a quite, it's something that probably we didn't expect at the very beginning, but it's something real and something that happens. You might see increase of pressure above the injection zone, even without any migration across the caprock. All right, so here I have the same results, but I plotted this a little bit differently. The figure on the left, let us see the changes of pressure, contour lines of changes of pressure, just to see how far these changes go from the injection zone. There are some sensors that can capture up to 1 kPa of pressure, but some other sensors, more standard sensors, capture up to 4 kPa. But the message of this slide is that we can measure those changes. If we had pressure sensors along the injector, we could measure those changes. Another important thing from these results is that also we can normalize these changes of pressure as the change of pressure above the injection zone divided the changes of pressure in the injection zone. And for the properties of this model that we chose, those ratios are in the order of a 1%. That means that the change of pressure in the above injection zone is going to be more or less like a maximum of 1% of what I would expect in the injection zone. So again, this might look a little bit small, but are definitely something that can be measured. Also, we can take advantage of this response, this increase of pressure, to track the CO2 plume. So, for example, in this figure, what we see is that the front of saturation of CO2 of 1% moves more or less at the same speed than the front of pressure in the injection zone of 1200 kPa. What that means is that if those fronts move simultaneously, by knowing what is the response I would expect above the injection zone with the ratio that we saw before, I could tell where the CO2 plume is. The figure on the right also help us understand this a little bit more. So how can I use these ratios to monitor where the CO2 is? Well, let's think about the monitoring layer closest to the injection zone. This is what we call AIC5. In this case, if we start monitoring the above injection zone change of pressure divided the injection zone pressure, at the beginning, if we know that it's around these values, we know that CO2 might not have arrived yet. We know that if it increases now in this region, that probably the CO2 plume is already there in that region. And also we know that we saw that there was a maximum before, that if the values go beyond this value that is what we expect, there is probably hydraulic communication. So here is now where we bring the other part of the problem. What if there is hydraulic communication? Is that good? Is that bad? What is going to be the result of that? All right. So here we add now a scenario with a leaky fault. For the geologists in the room, please ignore the lack of fault throw over here. We just wanted to make this model very simple and add a fault here in the model to see what would be the response. All right, so we're going to do the same thing, but now we have a leaky fault. So this is what happens to the CO2 plume. At the beginning, it's more or less as we expect, but then finds the leaky fault, and then goes through the leaky fault and goes to the monitoring layers. So the question is now, all right, what does that look like? What is going to be the pressure response along the injector? Here, there, 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 and there. And this is the result. Here in the solid lines are the results with the high permeability fault. Here with the dashed lines are the results with the fully covering caprock and no hydraulic communication at all. And you can see they're quite different. Notice that we have a logarithmic scale. So getting to know these two possible scenarios is very informative to get to know what might happen in a real field. Because as the results show here, if we have a hydraulic communication, the increases of pressure are expected to be at least 10 or 100 times bigger than what we would expect just with the poroelastic deformation. But it's important also to know that even in the absence of hydraulic communication, we are going to have a slight change of pressure, but it's very important to know how much. Another takeaway from this message from this slide is that notice that if we had a good model that could tell us that we have a high permeability communication, we could tell after 10 days in this case that there is a significant difference between what we expect with fully covering conditions and what we have with a high permeability fault. Just in 10 days, the difference is quite large. However, at 10 days over here, if we were to monitor CO2 composition at a monitoring well, I will have to wait at least 100 days to see the CO2 arrive. If CO2 goes through the fault, that's another thing. It's going to go through the fault or not. But if good, it would take at least 100 days for that, for me to get a proof that CO2 really arrived. So this brings another opportunities. Here you see the results of change of pressure in the injection zone and above the injection zone everywhere. And the idea here is that you could use the same principles that we have discussed before to place monitoring wells, several vertical, and that's kind of expensive, but also you could put a horizontal well in some formations above a critical reservoir and monitor those changes of pressure as a function of space. If you had enough sensors, you can conduct an inverse analysis and tell where your high permeability pathway is independently of any assumptions that you may do before on whether if you know or not if there is a high permeability pathway across a caprock. So we also extended this case of default to other cases. Like, for example, what about instead of a leaky fault, we have a sealing fault? What about if we have, instead of a leaky fault, an abandoned wellbore that also leaks? Or if we have a leak injector? Or what happens if we add a second injector nearby? And the response is going to be quite different. And that's also promising in the sense that with this type of analysis, also we can capture the signature of what we could expect with different cases. All right, now reality is a lot more complex than what we showed here before. So now, in the light of the what we have seen before, let's try to understand what happened in the field in other cases, and let's start with the first one. Well, for our first case, we see that there is a steady increase of pressure with time. That might indicate that either there was a small migration of the fluid through this wellbore, or particularly in this case, there are also some erratic changes of temperature that might have affected this monitoring well. But what is clear from the second well is that we do see these spikes of pressure with changes of injection rate that are telling us that particularly this well, it appears to have been very well sealed across the caprock. Also, the magnitude of the changes of pressure above the injection zone related to the change of pressure in the injection zone are very small, less than 1%, more or less what we expect for typical rock properties. This is another case in Germany in which there was an injection well right here, a monitoring well above the caprock, and what we see is that there is a steady increase of pressure during injection and also after injection. So what's going on here? Well, in this case, apparently there is a fault that communicates these two formations. So there might have been hydraulic communication in between these two formations. And actually, in the original paper, they say that it's very likely that there was a hydraulic communication. Also, the changes of pressure above the injection zone related to the changes of pressure in the injection zone are a little bit larger than 1%, not too big, but larger than 1%. And in this case, you may ask yourself, well, is this going to lead to a CO2 leakage or not? Because eventually that's what we want to know. And in this case, it's not really straightforward to say that, because the fault is also kind of like behind a top of a dome. So in some cases, we might have hydraulic communication, but that doesn't mean the CO2 is going to go through. The CO2 has to hit the hydraulic communication path to go through that. But in some cases, also may be beneficial to have a hydraulic communication, because that's what is going to let us inject more and quicker and have higher injection rates. If we have a very highly compartmentalized reservoir, that's sometimes not going to be good, because as soon as we start injecting, the pressure in the injection zone is going to increase very quickly. So the takeaway message now from this test is that also this method can help us quantify what is the hydraulic communication with other formations, and also can help us predict or better predict compartmentalization in a formation. This is another case which is not really above injection zone or above the caprock monitoring. It was injection monitoring, pressure monitoring in the same injection formation, but at different levels above the injection point. And as we would expect here, there is a very strong hydraulic communication. Changes of pressure in points above the injection point are in the order of 5 to 35% of the injection pressure. Let me go to the next one. This is another case in Australia where there was an injection zone, and there was monitoring above the injection zone, but within the same unit. There were some seals, but they weren't that thick, and there weren't that obvious seals with very high clay percentage. Also, for the seismic people in the room, you might see that there are some signatures over here that signal that something is not continuous. Well, the data in this case shows that there was a large hydraulic communication in the injection zone and above the injection zone. Again, this is the same unit. There is a bigger caprock above. But anyway, the changes were in the order of 17% above the injection zone related to the injection zone, which is showing that there's quite a significant hydraulic communication. And in this case, there is actually a fault in that place. And they did seismic monitoring. They showed that most of the CO2 plume remained within the injection zone, but there might have been either brine that flew that went through the fault, or even some small quantities of CO2 that might have gone outside this horizon, this sequence. But again, there is a top seal which is containing everything. All right, so I think I'm running out of time here, so I'm just going to go to my conclusions. Even if in the absence of any hydraulic communication with a fully covering caprock, we can expect changes in the pressure above the injection zone of about 1%. That's fine. However, it is important to know that if we have a hydraulic communication, those changes can be 1 order of magnitude or 2 orders of magnitude higher. And that's very important to know to diagnose if there is a hydraulic communication or not. And it is very important to do that to quantify whether there is hydraulic communication or whether there is a potential leak maybe above the caprock. That depends on many other things. And in order to predict this, you need a fully coupled poroelastic model of the entire storage complex to make an accurate prediction. Otherwise, you cannot do this. Without the poroelasticity coupling, you cannot run this type of simulation. So last, I would like to acknowledge the fund that made this research possible. Also, let me acknowledge again my collaborators from Chao-Jin Zheng and also Mathieu Van Damme and Jean-Michel Pereira from École de Pont. Also, I'm going to take here a few seconds to tell you that we're doing a lot of great research related to carbon utilization, storage, and transportation. And if you want to know more details, please send me an email. I'll be glad to talk to you more about opportunities for research in this area. And also, I'd like to advertise a little bit my geomechanics notes, which are available at this link. If you want to learn geomechanics, I think this is a good start. And also, if you want to check explanation of all those notes, I encourage you also to check my YouTube channel, where I have lots of videos related to geomechanics. I have even one playlist which is just about poroelasticity, in case you want to know more about that. All right, that's it. And thank you very much, Hadi and Sebastian. And I look forward to answering the questions of the audience.
Thank you very much, Nicolas, for this very nice, informative presentation. I see already plenty of questions posted. So to save time, Sebastian, please.
Yes, thank you very much, Hadi, and thank you also from my side, Nicolas, for a really nice talk, and also advertising your channel and all your free online open access resources. Pretty certain they will be heavily used by some of our members from the audience. So Hadi said plenty of questions. I'm going to try and sort of start a little bit at the front here.
Sebastian, maybe we can check if Nicolas sees us. Do you see us now?
Yes. I just stopped sharing my screen. I can see you,
yeah.
And I can see also the comment that just popped up.
Okay,
great. So Olarindra, who's a former head Watt graduate, good to see you, Olarindra. Yes, how far away from the well can you detect the pressure changes and CO2 saturation front? What is your view about incorporating timeless seismic data to your work?
Okay, so there are 3 questions here. So the first one is how far we can detect the pressure changes. So that would depend on the quality of the pressure sensors. There are some sensors that can go up to 1 kPa precision, and most common sensors will go in the order of 4 or 5 kPa. And for example, for our case, that meant about we could see changes of 4 kPa at more or less 900 meters. But that depends a lot on the properties of the rock. So there is no just one answer for that. But I think we could say several hundred meters for measuring those changes of pressure. The second one was about the CO2 front. How far we can measure changes of CO2 saturation. And then that depends a lot on where the CO2 plume goes, and whether the CO2 plume strikes your well or not. If you have some CO2, then also that depends on the resolution of the sensors that are capturing the CO2. So that's a lot harder to answer. And the last one in there was about combining seismic. So that last study that I shared with you from Otway, Australia, they did seismic, and they also have these pressure monitoring signals. Um and Actually, that's a study that was pointed out by a reviewer, and which I'm investigating more now. And in order to compare, one to one these two models, we'll have to build a model particularly for that place to make a prediction, and also to compare what we see with seismic, what we would see from the pressure monitoring for that particular place in Australia.
Thank you. I'm going to stay with a question from Olarinder, and actually I'm going to ask you two questions because they all sort of touch upon something you mentioned, the CO2 saturation. So Olarinder asked, how about incorporating repeat pulse neutron log measurements with this pressure measurements to separate the pressure effect from the saturation effects? I'm going to add a second question on this, if I can find it. There's so many questions. Yeah, so, and Abdul Rahman asks, thank you for the presentation. The first observation where they study pressure is, how can we say it's not due to gas adsorption? Caprock can be strong adsorption. So how can we quantify what is gas and gas effects versus what are other pressure buildup effects?
Okay, the first question about the neutron logs, that's very good to mention that in the motivation field case study that I shared with you, they did have this type of measurement. So they did monitor CO2 saturation with the neutron logs. The pressure monitoring was one of the other types of monitoring that they did. And in this case, they did observe the CO2 arrive at the injection layer, but not further above. Also, combining these to the comment of seismic, sometimes some of these methods, they have a very low resolution for, or a low precision for low saturations of CO2, which is another challenge. And the other question about the absorption. So that's one of my favorite topics. Actually, I'm writing a paper right now about absorption in mostly in organic rocks. Gas absorption will produce a change of stress in the caprock, but not a change of pressure. So that's another reason why we should monitor changes of pressure in sandstone or in informations without much clay, because where we're changing, remember that we're monitoring is a change of fluid pressure. If we were to change or to monitor a change of stress, then that's where we will see the effect of gas absorption on a change of stress, or what is called a swelling stress on the shale. But that would be something different, and that could be another type of monitoring, stress monitoring instead of pressure monitoring.
Okay, very interesting. Staying on the topic, so what can we get out of the pressure data? Elava Ahmed El Sheikh asks, how can we differentiate the pressure response of the AIZ, the above the injection zone? For example, how can we tell whether it's a leaky fault or a result of heterogeneity?
Okay, so for the base case that we model, the changes were quite different, and we just by the magnitude of the pressure we could tell whether there was a hydraulic communication or not. In this case, if we add heterogeneity, I don't think the results would change much, because heterogeneity is just going to change the field of pressure in the injection zone, but it's not going to change much the the magnitude. I think you refer to heterogeneity within the reservoir.
Yes. Yeah.
And if the heterogeneity, we think it at a larger scale, like for example, having some caprocks that thin out and they are not a seal anymore. Well, that's a hydraulic communication, and this type of monitoring should be able to capture that too. But
Yeah,
the differences are quite striking, and what is good, what I think is good.
Patrick Corbett, and I've worked with Patrick and with some PhD students on this. So this idea of geological well testing, if you have your pressure build-up transient and you try to calibrate that data using sensible geological models during production. So this would be almost the inverse. You're doing the injection of CO2 and you use the pressure transient data, the pressure signals, together with some sensible geological model to try and understand something with the monitoring data to understand how the subsurface behaves. And I think that'd be really interesting to do. Back to our audience. So Idris Buka says, great talk. Can't these pore pressure changes and the adverse effects be mitigated by simultaneously producing brine from the reservoir?
Okay, the answer is yes. So if we don't have changes of pressure in the injection zone, or if these changes are very small, then we will not see the changes of pressure above the caprock. The changes of pressure above the caprock are proportional to the changes of pressure in the injection zone. So if you don't change much that pressure in the reservoir, also you won't see any changes above.
Then that's an economic question. If you can afford drilling where it's produced the brine and you potentially create other leakage paths along those additional rates. Kishan and Leila have some very similar questions. Again, I'm going to read out both of you. They're all around the cyclic loading. So Leila asks, thank you for the interesting talk. How would the study help to make sure hydrogen would not escape the reservoir if being cyclically injected and produced? Very similar. Kishan says, thank you for the presentation. Very informative online YouTube lectures. How can we assess the storage safety under plastic deformation motivated by cyclic loading? So what would happen if you inject, produce, re-inject, produce, rather than just injecting?
Okay, well, so let's go to the first one for the hydrogen. Actually, I didn't think about that, but this also could be a good opportunity for monitoring integrity of seals for hydrogen. And going to the second one for the plastic deformation, notice if we see some of the results that I showed today, some of the strains are very, very small. We're talking about strains which are less than 1,000 or 10,000. So most of these strains above the injection zone are going to be mostly elastic. So they are going to be recoverable. So plasticity should not have much of effect on that. Where we might have some plasticity will be in the injection zone, where we might have larger changes of pressure. If there is a reactivation of neighboring fracture, also that's going to bring some plasticity in. But if the changes remain small, this should be mostly elastic. That would be a good extension to work on these, including plasticity. That's a great point.
Thank you very much. I need to close very sharply today because Hardy is working from his office and he has to be out of his office at a very specific time. Otherwise, TUDEF is going to lock him in. So apologies to our audience for not taking more questions. Thank you, Nicolas, for a great talk again and for answering the questions. There are plenty more questions that we could have asked, but we don't want to have Hardy sleeping on the office floor tonight, the first day back in his office. So, Hardy, very quickly over to you for some final comments.
Thanks a lot. Thank you. And please, those who have still questions, get in touch with Nicolas for more questions, or get in touch through his YouTube channel, which is posted here. Also, and being highlighted in a moment. I'd like to take the chance and introduce the next speaker. The next week we are hosting Tara Laforce from Sandia National Laboratories. Tara will speak about Voronoi meshing to accurately capture geology in subsurface simulations. Until next week, the same time, 4 p.m. Central European, 3 p.m. British. Now I should hurry up. Stay happy, healthy, and tuned into our channel. And we wish you all the very best in the coming days. Until next week, Thursday, we meet you again. Thanks a lot, Nicolas. Great talk and very good, engaging discussion.
Thank you. Run to the door.
Okay.
Bye-bye.
Thank you all. Thank you very much.
Thank you. Bye-bye.